Mhm. Okay, welcome everyone to the first session of our brand new seminar, which is in fact a continuation of the Proof Society seminar that existed during the COVID time. So in this edition, we will gather approximately once per month, hopefully, and invite excellent speakers. As the current speaker, Jeremy Avigad, will open this seminar with a lecture on formal verification. And so Jeremy Avigad is well known for his work in proof theory and in constructive mathematics. And he's currently a professor in the Department of Philosophy and simultaneously Department of Mathematical Sciences at Carnegie Mellon University. And in the later years, his attention was mainly drawn towards formal mathematics, and he is the director of the Hodgkinson Center for Formal Mathematics there. So we are very much curious about this recent advances in this discipline, which I must say, due to efforts of people like Jeremy and others, wide mathematical community is currently much more aware about this fascinating area. That is, of course, of central importance to the future of proof theory. So thank you for agreeing to speak and welcome. So please.
Thank you. All right, let me share my screen. Okay, so if everything has gone well, you can hear me, and you're looking at my screen at the slides.
Yes.
Yeah. Okay, very good. It is an honor and a pleasure to be here speaking in this Proof Society seminar. So as Lev mentioned, when I began my career, I called myself a proof theorist, firmly in the Hilbert tradition of reductive proof theory, so reducing theories to either classical theories to constructive ones, or a priori infinitary theories to finitistic theories, and so on. Since then, I've just led the most wonderful and charmed career. I've been able to explore wonderful and interesting things. And so much of it was really based on proof theory and the logical understanding of proof. So one thing I like about proof theory is that it gives you a means to look at informal proofs and understand them. So in my career, I've worked on proof mining, where you're looking at ordinary mathematical proofs with an eye towards extracting additional computational information or combinatorial information or quantitative information like bounds on rates of convergence. I've also had the opportunity to work in the history and philosophy of mathematics. Again, having a logical understanding gives you a means. So, for example, in the history of mathematics, it gives you a way of looking at the historical record and looking at the proofs and arguments in mathematics of the past, and thinking about the language that it uses and the assumptions and the types of inferences people carried out and how those have changed over time. In philosophy of mathematics, I've been interested in issues of mathematical understanding. What does it mean to understand a piece of mathematics, and what's the understanding that mathematics tries to convey? And again, having formal rules and formal representations at the base is really important. As Lev mentioned, I've long been interested in interactive theorem proving, so using proof assistance to formalize mathematical arguments. And again, so proof languages are interesting in that they're between formal proofs and informal proofs. So they're formal in the sense that they're they're processed by computer and they're checked by computer and they're compiled down to formal, conventional formal proof objects that are checked. But to be workable, the languages are meant to be close to informal mathematical language. They're meant to be at a level where mathematicians can actually write proofs and work on them. So that's yet another perspective on proof. I've been interested in automation and filling in details of proofs automatically and discovering things. And again, a proof theoretic understanding is important. And finally, one thing I'll talk about today is a place that I really never expected to go, but cryptography. And I've come to understand that cryptography is in a sense a kind of applied proof theory, in the sense that so many fundamental cryptographic gadgets are designed to convince, to prove something. So a digital signature is supposed to convince somebody that you are who you say you are, or that you have, permission to access certain resources, and so on. And over the course of the morning, we'll talk about what cryptographers called interactive proof systems, which are mechanisms, again, to convince people of things um, efficiently. Um, and so, these different perspectives on proof, they give you a sense of what it means, what the notion of proof means, what proofs are supposed to do. I mean, they're supposed to a proof is supposed to convince you of something, establish that something is true. Often, the thing that is established, you could just search for the fact or compute the fact or check the fact on your own. But proofs are supposed to do it efficiently. So they're supposed to save time or make it easier to confirm the truth of something. Sometimes proofs communicate additional information. So as I said, sometimes computational information or quantitative information. And sometimes in formal proofs, there's the things that sort of go beyond, the rules of inference in establishing truth. They're also supposed to communicate ideas and methods and different types of understanding. So I do like the fact that the Proof Society has taken this very broad understanding of proof. Um, and so, this feels right at home. So what I'll talk about today is a company called StarkWare that found me early in the pandemic. They found me and they had a verification project that they asked me to join. Um, and so StarkWare, it's a blockchain company. They're based in Israel. And what they've done is they've developed a means of running decentralized applications, so DApps, on blockchain more efficiently. They use that to run a cryptocurrency exchange, but more broadly, they have a platform that developers can use to run their own applications on blockchain more efficiently. Um, the methods are based on a family of programming languages called Cairo that I will tell you about. Um, and I have been using an interactive proof system, so a computational proof system called Lean, which is another project I've been involved in for a very long time. And we've been using Lean to verify their methods and their code. And if this means, so I don't expect that this means much to you right now. If this slide is totally opaque, that's okay. I mean, what I'm going to do is try to, hopefully by the end of this talk, this will make a lot more sense. Um, Right. But so, what we're doing is we're using the Lean Proof Assistant to verify the soundness and, in some cases, the completeness of cryptographic proof procedures. And just what I want to mention now, just to set the stage, is that so now there are two notions of proof that are kind of colliding or coming together. There's the notion of formal proofs in Lean, so it's a proof assistant that's checking proofs. But what we're proving things about are cryptographic proof systems based on the Cairo ecosystem. So we're proving things about proofs. So you're getting two applications of two notions of proof for the price of one.
So kind of reliable proofs are needed in order to verify the unreliable proofs.
That the proofs, yeah, exactly. That's exactly right. Or that the proofs mean what you think they mean. Yeah. And
Okay,
yeah.
sorry, can I so the idea is not how say to introduce somehow lean proofs into into this business, into cryptography, but rather kind of verify cryptographic procedures with using lean.
Right.
Right.
That's exactly right. So,
and but that question, but how do you know that lean procedures are somehow better than cryptographic procedures? So is it assumption?
Yeah, so let me tell you a little bit about interactive proof assistance a little bit later in the talk, and then maybe if it's not clear, you can come and ask the question again. But computational proof systems are designed to give you sort of so what they do is you state a theorem, you prove it. The proof is checked down to the primitives of an axiomatic system, right? And there are various ways of ensuring. So typically, the axiomatic system is tried to be, kept as simple as possible. There is a small trusted kernel in the program that does the checking, that is written very carefully and gives high confidence. Moreover, many systems can output their proofs that can be checked by independent proof checkers that other people can write. So there are various mechanisms that people use to ensure the kind of the reliability of proof assistance. But I will say more. I will say more about that. So maybe we can talk more about that later. Right. So let me tell you what, give you an outline for the talk. So I'm not assuming that you know anything about blockchain, so I will say something about that. And I'm not assuming that you've, seen interactive proof assistance before. And so again, by the end of lecture, you will have seen one. So these are the two, this is setting the stage for the two components. And then I'll talk about the Cairo verification project, the way that these two come together. I'll give you a high-level overview of some of the ways that we're using Lean to verify these blockchain applications. And then insofar as we have time, and then I'll talk about specific verification projects. So the three at the bottom are specific aspects of projects that we have done. And I don't know that, it's, I've got lots of slides, but the nice thing about it is I can talk for as long as people are interested. And then I can, as long as I get through the first three sections, you'll have you'll have the general idea of the talk. I'm happy that you're interrupting. Please do. I'd like to keep this talk informal. It's hard to give an online talk, and so when you speak up, it's nice to know that that someone's still there and people are still listening. So please don't hesitate to do so. Okay, so now to the first part. Let me tell you about a little bit about blockchain. And when I first started the project, blockchain, it was mysterious and opaque to me, and scary and frightening. I've come to now it doesn't, now it seems, kind of familiar. Part of the reconciling myself to blockchain is that you really don't have to understand how it works. You can treat it as a black box that just has a certain type of functionality. And the functionality is that, there's this magic ledger in the sky, where things are written down. And when things are written down, it is more and more things are written down, but nothing is ever deleted. So there's a complete record of everything that's been written down since the beginning of the chain. And the other twist is that, not anybody can write anything, right? There are rules, people have permissions that enable them, to add things to the blockchain. So, for example, if you're using blockchain to keep track of a cryptocurrency like Bitcoin, I might have a certain number of Bitcoin, and so that will give me permission, to transfer to Bitcoin to you. So that will sort of let me write something to the blockchain that alters, the amount that I have and the amount that you have. And blockchain, it's kind of the whole enterprise is, I think of it as kind of a funny mix of anarchy and capitalism, in the sense that, the anarchy comes in is that, you're really trying to get by without governments, without institutes, without, institutions, without lawyers, without courts, everything is supposed to, no government, right? It's supposed to happen on its own. But the idea is if you let people come together and kind of interact in commerce and trade on their own, then, well, there's this fantasy that everything's going to work out well. But what blockchain is supposed to do, it's supposed to support that by allowing these interactions and exchanges without any governments or institutions involved. And how it works is, again, that's a topic that I'm not the right person to talk about. There's a lot going on under the hood, but it has to do with, so first of all, decentralized maintenance. So so that it's not, any one person maintaining the ledger. It's lots and lots of people and lots of computers across the planet are maintaining the ledger, right? So it's kind of shared and distributed. But to prevent, anybody from trying to take control, it's hard, it's work. You have to do something to make a change, and you have to do something to convince others to go along with it. And so there are breaks that make it hard or impossible for anybody to, any one or small group of people to hijack the blockchain. Because it's work, because you have to do something, it's costing computer power or whatever. There are incentives for you to do it. And then there's kind of cryptographic magic that again gives certain people control over certain resources and so on. So this was kind of stage zero of blockchain technology. So with the advent of Ethereum came the notion of a smart contract, which was kind of the next advance. And so what a smart contract is supposed to do is this. So suppose, Lev and I agree to exchange. I'm going to give, him one of my Bitcoin, and he's going to give me, some of his cryptocurrency in exchange. And we talk over Zoom and agree to that. And Lev transfers his cryptocurrency to me, and then I say, "Ha ha! Now I have your cryptocurrency, and there's nothing you can do about it. I failed to come through." Lev might want to call the police or, go to the courts or sue me or, invoke some other, get the lawyers on me. But the blockchain, the ethic is like, no, we're supposed to be able to do this without any of that. So what a smart contract allows us to do is put a contract on blockchain. So what I do is I put one of my coins in escrow, right? So, until the end of the day tomorrow, I can't touch it. It's there. And the smart contract says that if Lev, transfers a certain amount to me, by the end of the day tomorrow, then automatically my coin goes to him. And otherwise, nothing happens by the end of the day tomorrow, it goes back to me. Right. So we have this contract that we put on the blockchain. It's public. I can see it. Lev can see it. We can look at it. We can inspect the contract and agree, that it does the right thing. And once it's there, it cannot be revoked. I cannot get my coin back, before the end of the day tomorrow if Lev does what he says. It just happens, right? It's part of the blockchain magic, right? And again, it's a powerful mechanism. You can use it for contracts and auctions and various types of exchanges and trading and, selling concert tickets. And you can have voting schemes that, will you can put something on blockchain that, everybody votes. They put their vote on blockchain and the thing is just decided. All happening without governments, without lawyers, without courts, without, Visa and corporations and so on. And again, how it works you can just take this as a black box. You need programming languages and ways of running them on blockchain and mechanisms for that. And, for the purposes of this talk, you just don't have to worry about the details.
So what happens if one side does not fulfill its obligations according to such a contract?
Yeah, so typically what the smart contract will say is it'll put a time limit.
Mm-hmm.
And we'll say that, if at the end of the day, nothing has happened, you give me back the blockchain. And then the state of the thing, I mean, the smart contract is still, kind of sitting on the blockchain. It's been published,
Okay, so
but it's inert.
It's part of this contract that
it goes all into the contract.
Prescribing what to do in this case. Okay.
Yeah. Yeah, I mean, and there are these DAOs. There, people will set up kind of organizations with all kinds of bylaws and so on that are all kind of written into the smart contract. Right? And this is actually part of the scheme. So so the contract is only as good as the smart contract and the code that implements it. Billions of dollars every year are lost because people will put on faulty contracts and people will find ways of hacking them and getting unexpected results, which is one of the reasons why verification of smart contracts is such a big industry and for systems like Lean. But I'm getting ahead of myself a little bit. There are limitations to the method. One is that it's expensive to run code on blockchain, essentially because everybody that's maintaining the blockchain has to execute the code. So it's not that it's just running once, it's running zillions of times. Everybody has to run it and come to consensus about the result. And so you're charged for it, for every execution step. You pay a price to have your code run on blockchain. And then it's also slow. And so, I've heard statistics. No, I don't remember the numbers, but Visa will perform tens of thousands of credit card transactions every second. And that kind of dwarfs the kind of volume that you can do on blockchain. And so there's this idea now on blockchain of using layer 2 solutions, which is you kind of limit the amount of you try to do as much computation as you can off chain, and then you minimize what actually has to be computed on chain. And that's what StarkWare is all about. They use ideas from complexity theory, interactive proof systems, to a very powerful, to a very powerful effect. Okay, so that's the idea. And so here's what their approach is at a high level. And again, I'll give you more details later, but here's just a kind of a high level overview. So they have actually a family of programming languages called Cairo. And the idea is what Cairo lets you do is you can write programs in such a way that if the program runs to completion, it sort of guarantees that a certain result holds. So in other words, we write the program in such a way that it does a computation. If the result checks out, the program just terminates. If it doesn't, you say the program just crashes. And so what that means, the proof what I'm trying to prove to you is that the program runs to complete. If we both look at the program and agree that it behaves as it's supposed to, then running to completion means, that my claim is true. So now my goal is to convince you that the program has run to termination. And they use cryptographic magic to publish short probabilistic proofs that the programs run to completion. So you don't get an absolute guarantee, but one that holds with very, very high probability. And this is what comes out of the proof complexity, or the computational complexity of the 1990s. So interactive proof systems and zero knowledge proofs, and so on. So this is something I will come back to and talk about more later on. But the short story is that they have a scheme that lets you publish certificates on blockchain that guarantee that a certain program has run to completion. And the certificates are quicker to check than actually running the program itself. So it's faster than having everybody run the code. They just have to check a shorter certificate that that's the case.
Mhm.
So far so good?
Yes.
Okay. So that was the first part. So now you have a sense of blockchain and smart contracts. Now let me talk about interactive proof assistance and lean.
So maybe one question before we begin. So the last slide that you talked about. So this use of cryptographic protocols is essentially in order to spare the resources needed for the blockchain to run the full computation, something like this. Right?
That's exactly it, right? So I'm publishing a short proof. I'm saying, don't worry your pretty little head. You don't have to run this program. I ran it. Trust me, I ran it. And I'm publishing a short proof that convinces you that I really did run it and it really did terminate.
There's still a probabilistic, so to say, proof that it holds with 1/1,000,000% error possibility or something like that. So.
Yeah. So the models in the 1990s, and I will come back and talk about it, but the models in the 1990s were based on coin flips. So the idea is I send you some information, right? I make certain commitments. You flip a coin or flip multiple coins and ask me questions. And if I can answer all the questions that you ask that I couldn't determine in advance because I don't know your source of randomness, then you're convinced that it's correct. The coin flipping is now replaced by cryptographic hashes and so on. So in other words, something is generated that you couldn't have predicted ahead of time, but it roughly has the same functionality.
Okay.
Yeah, can I just also clarify this point? So do I understand that correctly, that the idea to use, say, lean for verifying these protocols, right, is somehow theoretically is based on this assumption that somehow lean is a type theory, and type theory is kind of the language we are writing. So it's something like corresponding to logic, and that's why we verifying this sort of probabilistic messy protocols with logic. So behind there is this strong epistemic assumption about kind of fit between the logic and lean. Is it
Yeah, I think
something
that's right. I mean, so I haven't talked about lean
okay.
yet, and I'm about to.
Yeah.
But think of lean as just mathematical proof, right? So you have this
Okay.
complicated, protocol, and you have this code that's running, and right. And
Right.
if you want to be convinced, the best I can do is give you a mathematical proof. But mathematical proof is if I sort of send you a LaTeX document, you read it, and then it's work to get through, and there may be mistakes that we both miss, and then we have lean to actually check the details of the mathematical proof. So your proof assistant is the language of mathematics. Anything that we can express mathematically, we should be able to do that there, and then we're using it to reason about these crazy protocols and programming languages and so on.
Okay, thanks.
Yeah. So let me tell you a little bit about proof assistance. Right. And then once we have those two worlds, we'll talk about how they go together. So proof assistants fall, in computer science into a realm that computer scientists called formal methods. It's the phrase refers to a body of logic-based methods that are used to write specifications for computational artifacts and systems, so hardware, software, network protocols, cryptographic protocols, and so on. Right. And then you want to verify that, the hardware does what it's supposed to do, or that the software does what it's supposed to do. In other words, that the design of the hardware meets a certain specification. So you have a model, a description of the hardware, the software, the protocol, and you have some property that you want it to have, and you want to verify that that's the case. And the methods are called formal methods because they're based on formal logic. So you have formal languages to write the specifications, formal semantics that tell you what they mean, and then formal rules of inference that, in your reasoning processes, are supposed to guarantee that, that your claims are, that when you claim that something meets the specification, that it in fact holds. So you want sound rules. And the idea is, we've known, so within formal methods, there are multiple approaches. One approach is to use interactive theorem provers or proof assistants. We've known, since the early 20th century that mathematics, broadly speaking, can be formalized. And the idea is now we can use computers and computational proof assistants to do this in practice. So you can essentially use the computer to construct formal proofs of substantial mathematical claims. And as I said before, when you're successful, often buried in the machine, there is a description of a formal axiomatic proof that you can export and somebody can check independently. And so in the beginning, proof assistance, the idea was formalizing mathematics, verifying mathematics. Around the 70s, there was interest in using them for hardware and software and system verification. People realize, and there really isn't a sharp distinction between them. I mean, again, if you're trying to prove that that a program meets a certain specification, well, that's a theorem, right? You have a description of the program, you have a statement that that running this program has this result, and that's just a theorem that one is trying to prove. It's different from proving that there are infinitely many primes or something like that, but in principle, they're just mathematical statements, and you're looking for proofs. And so here I've listed historically some of the major proof systems for mathematics. There are lots of them out there, and they're all wonderful, wonderful systems. These are just some that have substantial libraries for mathematics. Mizar, Isabelle, Roch, which previously called Koch, Hall-Light, and since 2013, Lean. And verifying mathematics, that's always been my main interest. But again, I tell people that for every one of me interested in verifying mathematics, there are just hundreds of people verifying now hardware, software, protocols, and so on. It's a much bigger industry. A few years ago, as recently as 2017, there were really very, very few mathematicians using formal methods at all. So it was really the industry was filled with computer scientists. Even computer scientists were for fun or for whatever reasons they were formalizing some mathematics, but mathematicians it's really just a handful of mathematicians involved. And as Lev mentioned, I mean, the last few years have just been things have changed dramatically. It's kind of almost surreal the level of interest. So, Lean's library, MathLib now has almost 1.6 million. And every time I give talks like this, I have to kind of update the slide and look up the statistics and the numbers. But there's a large mathematical library. There's a social media channel that has now 11,000 people signed up. And in any 2-week period, there are about 250 people that are kind of logging in and posting messages. But there have never been high-profile successes and articles in Nature and the New York Times and Quanta. There are meetings, workshops, summer schools. So it's kind of a very lively time. And I don't want to spend a lot of time talking about this because you can find surveys and there's a lot out there on the internet. But this is
Jeremy, I'm sorry interrupting you, but just you are mentioning only Lean, while there are evidently other competing projects. This is just because of your personal experience, or there is some special reason?
Two reasons. So yeah, there are a number of proof assistants out there, and many of them still in active use and very lively used. Interestingly, Lean is the first one that has captured the interest of the mathematics community. So as I said, I mean, now there are a number of mathematicians involved, and overwhelming majority of them are using Lean. So really, it's the first one to really establish itself in mathematics. Yeah. But you're right. I mean, again, I should be careful. There are a lot of systems that are still out there, and they're all really, really wonderful.
Yeah, and some mathematicians certainly prefer some other, and actually for kind of principled reason, right? No, not just taste, right?
Yeah, so we could spend a lot of time talking about Lean and other systems, the differences between them. I mean, Lean is designed, and the library especially is designed for classical mathematics. If you're interested in constructive mathematics, Lean is not the system for you. There are also people. So there are systems, for example, for homotopy type theory that you can think of them as kind of alternative foundations for mathematics, but another way to think about them is they are synthetic languages that are good for very specialized areas of mathematics, like reasoning and homotopy theory and infinity categories and so on. So there's also interest in other proof assistants for more kind of specialized reasons. So if you've never seen a proof assistant before, I mean, you should. So what I want to do now for a few minutes is just kind of show you, show you Lean, and what it's like to use it. So what you're doing is what you're seeing now is Lean running in VS Code, the editor that's maintained by Microsoft. On the left, this is my proof document. It's talkdemo.lean. I'm running my proof. And at the beginning, I'm importing some files from the library, just so I have part of the library there to work with. And on the right, that's called the Lean info view. This is the system kind of responding to me. So as I move the cursor around, let's see, I'm wondering why it's not updating here. Let's try again. Oh, it's bizarre. Oh, you know what? Hold on. I'm sorry. I'm kind of struggling with the Zoom. Sorry. Did I lose? No, what's going on?
No, we do see your.
You do still see. Okay.
We do see it, and we see the mouse moving around. Oh yes, now.
Okay. Good. Okay. Good. Okay. Toggle the input view. Okay. Good. Yeah, okay, we're back. Okay, so so on the left, so for example, here's a definition of the Fibonacci function, right? It sends 0 to 0 and 1 to 1, and n plus 2 to, fib n plus 1 to fib n. But so, lean is, so when things have a computational interpretation, lean can compute them, right? So you can say, what's the 10th Fibonacci number? And lean tells you over here, it's 55. Or if you hover, there's a lot of information going back and forth. If you hover over squiggly lines, information pops up. So you can define functions. I mean, so computable functions, non-computable functions. I mean, you can write down, the function which is 1 if a Turing machine halts and 0 otherwise. So right. But when you define something that's computable, lean will compute with it. But you can also then state and prove theorem. So here I'm stating the simple theorem that if x is a real number, then 2x is less than or equal to x squared plus 1. And see, I'm just sort of looking for my notes. And so sorry. So here we're getting a warning. So sorry is a proof of anything. It's saying sorry. I'm not proving. I'm cheating. And lean knows it. It says it's a warning. It's saying that you really haven't proved this. But let's work on a proof of this together. So I'm going to put the word done because that just gives me an error message that it says I'm not done, but it prevents the error message from kind of being flagged somewhere else. So I'm going to prove this by showing that when you subtract one side from the other, when you subtract, let's see, the left side from the right side, the result is non-negative. And so I'm going to do this by applying a rule called LE of sub non-neg. Right. It says to show that something is less than or equal to something else, you can show that the difference is non-negative. And now lean is telling me that my goal is to show that this difference is non-negative. So what you should think of this is what we're doing is we're writing a little program, and this little program tells lean how to construct a formal axiomatic proof that its checker can check and verify as being a proof of the theorem. So, one thing we might want to do now is, see if we can copy that, is now to factor this to show that this is x minus 1 squared, right? So let's kind of state that as an intermediate goal. So that's equal to x minus 1 squared. And this is just a ring calculation. So there's a little bit of automation that will just kind of do the calculation. We'll apply the rules of associativity and and commutativity and move things around. Right, but lean can do that. So that's proved. Going back to the goal. So now let's kind of rewrite. Sorry. So let's use that identity to rewrite the goal. So now we need to show that that this thing is positive. And so, any square should be non-negative. We can ask lean, tell me, is there something that that I can apply? And lean says, oh, well, this fact will do it. So you can show that the square of, so you can show it by showing that x minus 1 squared is non-negative. There are lots and lots of ways to write this proof. There's also automation that's really good at showing things are positive or non-negative. It's called positivity. And so we're just calling automation to do it. And that's the idea. That's what it means to use a proof assistant. There's a library of facts. So for example, this LE of sub non-neg, if you hover over it, you can see the documentation. It says the theorem is that, to show that B is less than or equal to A, you can show that 0 is less than or equal to A minus B. And then, well, I mean, then there's this kind of crazy boilerplate. It holds in great generality, not just for the real numbers. So in fact, let's try this. Let's say R, say commutative ring. Let me say R is an arbitrary commutative ring. And now let me state the theorem. No. Oh, sorry. So it's telling me, yeah, what's the error message? It's mysterious. That failed to synthesize LER. What's going on? It doesn't know what it means for something to be less than equal to something else.
Commutative rings,
Because
yes.
it's a ring, right? So what I really want is an ordered COM ring. Oops. Ordered COM ring. And now, but positivity didn't work, but let's see if so that bit of automation didn't work for some reason, but, let's see what's going on. So the goal here is to show that x minus 1 squared, square. Oh, well, square, apply, sorry. Okay, well, maybe we'll come back later and try to figure out why. Let's say apply. It's giving me some find pound on egg. 0. Oh, interesting. Okay. Yeah. Okay. I don't know. So
Well, it gives you a good idea how the process.
of the frustration. Yep. Yep. So here I also demo. If we have time later and you're interested, we can come back and play around with it. We can prove that for all n, the nth Fibonacci number is so phi is the goal of 1 plus the square root of 5 over 2. Actually, I could have written and used the notation square root. Yeah, that also works. It's even prettier. But you can find the golden mean and its conjugate, and those are the Fibonacci numbers. And another example that we can play around with in a demo is just to apply the intermediate value theorem. But yeah, that's the idea. So now you know roughly what a proof assistant is. You state your theorems and you try to prove it. Okay. So we've done the first two parts. So now what I want to explain is how the two come together, right? The idea is now to use Lean to prove things about Cairo. So let me tell you that story. Okay, so here is the idea, right? You have to imagine that I'm a powerful prover and you're a resource limited verifier. I don't mean any offense by that. I just try to imagine the scenario. The idea is you want to be able to check things efficiently. I'm not too concerned about my resource. I can do a lot of work, try to, produce an efficient certificate, but we want something that you can check quickly to guarantee a claim. And so the first thing we do is we agree on a program in a programming language called Cairo. Okay, one of a family of programming languages called Cairo, right? Such that you and I agree that if this program runs to completion, then the claim is true. So, for example, if I'm trying to convince you that 2 plus 2 is equal to 4, we write down a program that computes 2 plus 2, subtracts 4, compares the result to 0. If the result is 0, it halts successfully. If not, it crashes. And you and I look at the program and we agree, you agree that yes, if this program runs to completion, then your claim is true. Then we have a compiler translate it to assembly code and then a machine code for a certain architecture, like a CPU. Okay. And so now I'm trying to convince you that this machine code runs to completion. Right? We started with a high-level program. Now we translate it down. So now my task is to convince you that the machine code runs to completion, right? And more precisely, what I want to convince you is, so since the machine code is going to refer to contents of memory, what I want to convince you is that there is a way of assigning values to the memory, extending what we agreed on. And there's the program in the memory, there's the input data, right? There's a way of doing that such that when you run the program, with the CPU, it runs to completion. And what we do is we write down a complicated system of polynomials such that the existence of solutions to those polynomials establishes exactly that fact. Okay, so we encode the claim about termination of the machine code to a claim about the existence of solutions to a family of polynomials. Okay. And then, Cairo uses cryptographic magic to publish to blockchain a short cryptographic certificate that guarantees the existence of solutions to this family of polynomials. So this is what goes on blockchain. This is the thing that you can check efficiently. And this is supposed to convince you that 2 + 2 = 4, that my claim is true. And if you're looking at that, you should be thinking, what? What, are you serious? I mean, this is really supposed to convince me of, I mean, there's this complicated scheme. So, if you're in the formal verification business, right, you ask questions, okay, what, what could possibly go wrong? And, you look at this, it's like, everything everything could possibly go wrong, right? So what to believe that this does it as it does. I mean, so first of all, we wrote this high level program, and my example, add 2 and 2 and subtract 4. Okay, maybe you can look at that. But if the program is doing something substantial, then you might worry, does this program really establish what it's supposed to? And especially if I wrote the program, I mean, that's even worse, right? You're looking at my program and yeah. But then the compiler translated it to machine code. Who knows what the compiler is doing, right? So, right. So you have to believe that the machine code reflects the high level semantics of the program. Then we wrote down this complicated system of polynomials that's supposed to encode the fact that the machine code ran to completion. And are you really going to trust that? And then there's this magic cryptographic protocol that's supposed to convince you, with high probability that there are solutions to these polynomials. Okay, so this is the kind of thing where you want formal verification, right? If I can give you a lean proof of all of these claims, right? And you believe you understand the statements and you believe lean as a checker, then you have a lot more faith that the system is doing what it does.
May I ask at this? Of course, there are a number of questions. It's too early to ask, but why here specifically in this item 3, polynomial encodings are used?
Yeah, that's just because so I will say a little bit more about the protocol, but that's
Is it a kind of propositional proof system, but or algebraic proof system or something?
It's like an algebraic proof system. That's just what the cryptographic protocol is good at establishing. There's a cryptographic gadget that is designed to do exactly that. It's designed to convince you that there exist solutions to polynomials, roughly speaking. And so that's the hammer you have. That's the tool, the cryptographic tool. And so now if you want to prove other things, you have to reduce them to that.
So to understand correctly, this polynomial thing is a kind of part of this cryptography, right? It's not part of your verification.
So cryptographic protocol, what it does is it serves to convince people that that of the existence of solutions to polynomials, and then to convince people other things, you have to do the encoding. So there are 2 steps. You take the claim you want to prove, you translate it to a statement about polynomials, and then the cryptographic protocol establishes the claim about polynomials.
And how it's cryptography, so it makes it has kind of secret code or something.
Yeah, so I'll say a little bit more about that, but not much. But I'm here I'm not the expert, but there are fundamental cryptographic primitives that it's I'll say, well, I mean, so one way to think about it is here is so suppose we have a complicated polynomial expression. Saying it's just one variable x, and we know it is, degree, most 200, but it's really complicated. It's, kind of written with products and, in a way that's really hard to compute and evaluate. And suppose I claim to you that it's the 0 polynomial. I say, trust me, I did this whole calculation, it's the 0 polynomial. Well, you don't want to trust me, but how can I convince you, or how could you convince yourself efficiently that this polynomial really is the 0 polynomial? Well, just pick a number of random and plug it in, right? I mean, the thing has at most 200 roots. If you do this over a very large finite field, you can do this calculation. And if you just pick a few values at random, if there are 2 to the 256 elements in this field, if you do it a few times and get 0 every time, then with very high probability you're convinced that the polynomial is 0. And so this is the kind of trick of these are the kind of tricks that these protocols use to kind of establish something, not with absolute certainty, but with very high certainty.
Okay.
Yeah.
Thanks.
Okay. So the projects we've done are so first of all, we verified the polynomial encoding. We've verified, we have a compiler that will compile programs, and as it goes, it produces lean-checked proofs that the machine code meets the high-level specification. And then for particular programs, you can then take that high-level specification and use that to prove your own specification. Okay. So these are all projects that that I can talk about. Again, depending on how much time and energy we have, but these are the projects. The last part, verifying the low-level cryptographic protocol, um, uh, was out of scope, so we did not do that. But this is another thing that people do. So there are formal verifications of various cryptographic protocols. I mean, we used one, Starks, that was, it's the protocol has been published, it's been peer reviewed, and so on. So the company, this was kind of the least of their worries. They had faith in the cryptographic protocol. Um, um, but again, that's the kind of thing that one can verify as well. But the company was much more worried about all these steps. And so this is where we focused our efforts. Okay, so let me think where we are. Okay, so yeah, so just right. So just to summarize, what we've done. So first of all, we've proved in Lean that of the correctness of the algebraic encoding of execution traces. So in other words, we've proven a theorem that I can show you of the form that there's a very long list of polynomials, and we've proved a theorem that says roughly that if so given memory extending a certain program, uh, uh, and given that over that memory the algebraic the polynomials have a solution, uh, uh, then the program runs to completion. Okay, so it's a complicated theorem about relating the polynomials to the execution traces. As I said, we've built a verifying compiler for one of their languages, Cairo 0, now called Cairo 0, that enables us to write a high-level program. You hit a button, it gives you a high-level description of what the program does and a lean proof that the machine code satisfies the high-level specification. And then, so now for particular programs, so for example, they've written uh, uh, a software library for validating signatures with elliptic curves. We've then taken the high-level description from the compiler and proved that those imply that the claims about elliptic curve computations hold. Right. So we've proved in particular cases that the high-level descriptions imply the specifications that we want. Okay.
What kind of specification language did you use to describe this high-level Cairo 0?
So I will show you, but that's all done in Lean. Okay, so all the specifications are written in Lean. The description of the execution. Well, yeah. So let me. But yeah. So I will show you. So everything is. So Lean is the proof assistant of choice in which we're writing the specifications and writing the proofs and checking the proofs. Okay.
Excuse me, may I ask a question?
Yeah.
The Cairo 0 as a compiler itself is written in Lean, or it is also written in some other language?
No, so this is another interesting aspect of the project. So Cairo 0 was written in Python, and it's funny, the language itself has kind of Python-like syntax and so on. They've since moved on to the next generation language, which is now called Cairo, that is written in Rust and has more Rust-like syntax. The interesting thing is that when we started the project, the company was already working on the compiler. They had a large team of engineers working on the compiler and writing it. We're proving something about a compiler while they're writing it, and we had no control over it. So this was this amazing. I mean, it just amazed me that it worked. But we managed to make it work. What we were able to do is go into the compiler and just add hooks to get it just as it was going, just to log enough data so that we could reconstruct a proof afterward. Um, and so, yeah, so that is an interesting point. So it was really people in the I mean, we did have communication, with them, but really the compiler, they were not interested in the verification. I mean, they were happy to know that was going on, but they were not interested in the verification effort. They were trying to get their compiler and their libraries built. And so, yeah, that went on independently. So we're using we're trying to extract proofs from a compiler that another team is working on.
And so on this level, it seems like the project mostly used Lean as purely formalization language rather than using its computational aspect to write executable code.
That's right. That's absolutely right. So there are, yeah, maybe I'm getting ahead a little bit. So for projects like this, there are different approaches that one can take to verifying that compilers do what they're supposed to do. So the approach that we took is called a proof producing compiler. You have the compiler do whatever it does, and then every time you run it, it does a compilation. You also make it produce a proof, on a case by case basis. Every time you compile a program, it should produce a proof that the program meets the specification that you want. Another thing you can do is you can prove the correctness of the compiler once and for all. Right. So in other words, you can write down a specification of the high-level language, the low-level language, and prove once and for all that whenever I run this program on a high level, the compiler on a high-level program, the output meets its specification. And the most famous example of that is a project in Coq called CompCert, which verified the correctness of a C compiler. Even CompCert did have for some aspects, there are certificates that are generated and checked on a case-by-case basis. So there's kind of a mixture of proof producing. But so there are different approaches that one can take. And that's maybe, for the questions, that's something that we can discuss, the different approaches and advantages. But this worked very well for our purposes.
So in general, this case-by-case approach to compiled programs is somehow easier to implement or to verify in.
Yeah, so we're sort of getting ahead, but so what? So the reason it worked so well for us. So challenges with the first one is that it's brittle, right? If the code of the compiler changes a little bit, you have to kind of rewrite your proofs. I mean, it is nice that once and for all you have a guarantee that this compiler will always run and succeed. With our approach, what we could do is we could handle aspects of the language bit by bit. So basically our code would run and it would try to generate a proof. And if it failed, it would just fail and crash and so on. But what we could do is then we could start small and just keep working and build our way up. We could get larger and larger parts of the language. We could check more and more programs. If we ever ran it and the proof failed, we could go in and look at why it failed and figure out how to fix it. But it was good for kind of building up piece by piece. And moreover, the compiler is not guaranteed to cover the full language, right? There are programs that we know that it just doesn't handle. So we could really focus on pragmatically on being able to verify the programs that we wanted to verify and kind of do it in a very flexible, piecemeal way.
Okay.
Okay. So yeah, and just so some additional information. So more precisely, Cairo is really an ecosystem. It's now a family of languages. There's the virtual CPU and the instruction set. There's an assembly language, which is very close to the machine code. Uh, there's a programming language, Cairo 0, that adds kind of variables and structures and function definitions and so on. So that looks more like a fairly rudimentary but conventional programming language. And then their next generation language, now called Cairo, has type safety guarantees. It's a much more robust language. Okay. Yeah, another thing that is interesting that I should mention is that, so as we've talked about, the successful completion of a Cairo program is meant to establish something. If the program runs and succeeds, then you know that something is true. Um, uh, so, people in the business refer to, when you have a system like this, the soundness and completeness used pretty much in the way that, we logicians conventionally use it. So soundness is the property that if this program runs to completion, um, um, then a certain property holds. Okay, so more broadly, that I may not make all the information public to you, but I have some additional information about what to assign to memory that makes this property hold. Okay, so soundness is that if the program runs, you guarantee that the property holds. From the company's point of view, they also want to know that their methods are complete, that if the property holds, that they can publish the certificate, right? They only get paid if they publish the certificate on blockchain. So the completeness is kind of the flip side. It's the guarantee that if the property holds, then the methods, in fact, will generate a correct certificate. We have done both from the point of view of convincing the world that the methods are sound, are reliable. Soundness is the more important property. But I will mention in passing that the company is also interested in the completeness question as well, which is something that we have also addressed. Okay. And let me just mention also that so not everything is public. There's a lot that's public so far. There's stuff that we're still working on. So, but already you can find the GitHub repository, a couple of papers, a new one that we just put on archive. That's basically an expansion of a conference paper. So, the stuff I'm talking about now you can find. If you go to my webpage and poke around, you can find all the links. Okay. So. Okay, good. So yeah, let's kind of recap where we are. So I've given you sort of the high-level picture of blockchain and publishing certificates on blockchain. We've talked about proof assistance, and we've talked about now the particular verification tasks. And so the three things that I can talk about now are kind of at the low level, describing, the CPU architecture and the encoding of execution traces, or the compiler that we talked about briefly, the proof-producing compiler, or then one particular application was verifying their library for elliptic curve computations. I think what I'm inclined to do is focus on just do the first one, because again, I've been talking for a while. I don't want to outwear my welcome, but just say a little bit about the first one, show you a couple of the lean specifications. So I think if we spend just maybe 5 or 10 minutes talking about the first one, and then call it a day.
So the third one looks like a kind of standard mathematical theorem proving or something like that, right? So
it is. So yes and no. So the there's a good story there too. So there is verifying the challenge is for elliptic curve computations is proving, the associativity of the elliptic curve law. That tends to be hard to do and hard to do formally and hard to verify. We're pleased that was done for us by other people in the lean community. So the mathematics of elliptic curves, we had that in the library, which was nice. And then the computations are, the encoding is, so this happens whether you're using Cairo or whether you're using a conventional programming language. You've got these computations, over large finite fields. You've got basically variables that can hold certain number of bits, and so you have these representations. Every element of the elliptic curve is it's a pair of x and y values, and each one is represented by 3 integers. And now you're doing these calculations and worrying about overflow. So there's kind of a fiddly computational task, which was really what they needed the verification for. So that's the nature of that. It's kind of verifying a very particular implementation of computations over 2 particular elliptic curves, and worrying about bounds and overflow and things like that.
okay.
So okay, so should we do the first one for? Yeah. Okay. Okay. So yeah, let's just do like I said, let's go 10 minutes and then call it a day. So yeah, the cryptographic protocols, they have colorful names. So there's one technology called SNARKs. They stand for Succinct Non-Interactive Argument of Knowledge, but I think the name is supposed to, remind you of the Lewis Carroll, The Hunting of the Snark. Um, there's the one that Cairo uses was developed by the founders. So Elie Ben-Sasson is one of the two founders. Before he founded the company, he was a worker in cryptography, and it started actually early on proof complexity. He did some early work. His advisor was Avi Vigderson, and they have some nice results in proof complexity as well. But that's called Stark, Scalable, Transparent Argument of Knowledge. And then sometimes you'll see the ZK put in the beginning. ZK stands for zero knowledge. Again, what comes out of the 90s technology is sometimes I can convince you that a fact is true without giving away any additional information about the proof, or so this is there are times when you want to convince. So for example, I might want to convince you that I know a certain password, but not tell you that password, right? Or I want to convince you that I have a certain amount of money in my account. I might want to convince you that I have more than $1,000 in my account, but not tell you how much I have beyond that fact. And so this is what the ZK is meant to do. But really, the name Stark, I think, so the company is called StarkWare Industries. And I don't know whether somebody told me this or I just kind of surmised it, but this is from the Avenger movies. So Tony Stark is Iron Man, and he has this big corporation called Stark Industries. So the Israeli company is called Stark Industries. So I think Stark is, it's kind of a nod to that. Anyhow, so what a Stark lets you do is, roughly this. Again, the details aren't too important, but let me just give you a feel for this. So you fix a large prime number p, and you take the finite field of integers modulo p. And what a Stark will let me convince you that I have a table of elements of that field satisfying polynomial constraints. And the idea is, so for example, the table, there are rows and there are columns. So for example, this polynomial might mention, variables in row I and I plus 1. And, the claim might be that this polynomial holds of every other row in the table. So, holds of the things in, rows 1 and 2, and then 3 and 4, and so on. So you've got tables and polynomials and you have tables and polynomials, and roughly the Stark gives you an efficient way of convincing somebody that that this algebraic fact holds. Okay. Right. Okay. So remember the task. So what I'm trying to do is convince you that I know of a full assignment to memory extending the part that we agreed on, and an execution trace of the CPU from the start state to the final state. The cryptographic magic will convince you that, I have a table of data that satisfies a bunch of polynomials. And so, again, like I said, that's the nail you want to bang in. This is the hammer. And so you've just got to translate this statement to that, right? So there is a method that, so this is, they call it the algebraic intermediate representation. They have a method of encoding statements about execution traces in terms of polynomials. They published this. They wrote a white paper that explained the encoding and proved that it was correct informally. And our task was to verify the proof. So, the CPU, let's see, it was a very simple register machine. There are 3 registers. There's a program counter, an allocation pointer, and a frame pointer. And, it's a very simple language. You can assert that 2 things are equal. So this is the assertion that if you take the value in memory at location X, and that's equal to the value in memory location Y plus 3, there are jumps, there are conditional jumps, there's a call, and there's a return. your reasoning, so everything in memory is a value in a large finite field. So you can do plus and times. There's no notion of ordering. You can't compare because it's, it's a finite field. But yeah, so that's roughly the low-level programming language. And so what we did, well, actually, I guess just in the last few minutes, let me just show you, not do it through the slides. But let me show you, here's the semantics, error encoding. Okay, so roughly speaking, let's see, instruction.lean. Let's see. No, wait, where is our instruction? There it is. Okay, sorry. So here is the machine instruction consists of 3 16-bit offsets, right? So that's bitvec 16. There's a 16-bit bit vector, and then there are 15 Boolean flags. Okay, and then the description of the okay, so that's what instruction looks like. At any point in the computation, right, there's memory, which is just at every field element, the addresses are field elements and the values are field elements. So the memory is just a function from a field f to itself. And at any point in the computation, the state is summarized just by the contents of the 3 registers. So there's a program counter, an allocation pointer, and a frame pointer. Right? So think of it as there's a stack pointer, a pointer to somewhere in memory where values are being allocated, and there's a program counter. And roughly is what you're looking at is kind of a, so this file is, it's not huge. It's like 118 lines. What it is just a specification of the execution semantics. So there's a way, so given the settings of the flags, there's, a way of computing the different operands, the operand 0, operand 1, and so on. So for example, there's a specification based on the setting of the flags and the contents of memory, what the next program counter is. And so there are 3 flags that specify either it's an absolute jump or a relative jump or a conditional jump or none of the above. So at most, one of these flags is supposed to be set. So if none of the flags are set, you basically go to the next instruction. And then, it tells you, the specification tells you, what an absolute jump does, a relative jump, a conditional jump. And moreover, the fallout case is if it's not any of these situations, you just crash. So that's what the none is. But so you have a specification of, what, so basically what this is doing is it's giving you a specification. Given an instruction I, given the contents of memory M, and given a register state S, it says what it means for T to be the correct next state. And the reason that this is written as a relation, so given, so it's next state I, mem, S, T, is that for some states, there may not be a next state. So this is the program crashing. And for some states, there could be non-determinism. So there might be multiple next states.
Okay, so just to step back a little, so what we are seeing here is a formalized in lean specification of that counter machine that you presented on the previous slide. So to say,
Exactly.
A very little machine with 3 registers and so on and so on. So, and this is a formal specification of
it's a formal specification. Yeah.
Okay.
And just to kind of jump over all the details, these are, so from the compiler, we had to generate this file automatically. These are the polynomials. Where are they? These are the polynomials in the encoding. Okay. And so when the Stark certificate is published on blockchain, these are the polynomials that people can see. Okay. And let me just jump to a final statement of the correctness theorem. Right. This was our correctness theorem, which, so the statement of the theorem is here until the by. Okay. Okay. And let me not go through all the details, but it says so. So here we have to assume that the field that we're operating on has a certain size. So it actually is most of the proof is independent of the size of the field, just as long as it's big enough. And roughly 2 to the 63, that's the number of bits in an instruction. So we need to know that the field elements are big enough to hold instructions. But roughly it says that given a table of data. Let's see. That's right. Well, roughly it says, given a table of data that satisfies the constraints, there exists an assignment to memory that extends the publicly, agreed upon part of memory that you and I have agreed on. And well, here's the important part. There exists an execution trace. So fin t+1 is just the integers from 0 to t, right? So this is a length t+1 sequence of register states such that, the first one in the execution trace, the program counter is the initially agreed on program counter. Similarly for the allocation pointer and frame pointer. So in the beginning, they both start pointing to the same thing. And moreover, the last one is the one that is claimed by the certificate. And moreover, for each intermediate one, the next state satisfies that relation. Okay, so the theorem is, again, we can talk about it more if you want more details, but the theorem is roughly given an assignment to memory satisfying all the polynomial constraints, which are summarized here, there exists a successful terminating terminating execution trace. Yep. Yeah. And the proof is, this just kind of summary. The proof is, kind of all these files, but you'll see, polynomials and theorems about if these polynomials are satisfied, then this holds. So it's kind of spread across all these files. And with that, let me see. Let me just go to a rousing conclusion at the end. Oops. So, okay. So just takeaway messages. In a sense, cryptography is a kind of applied proof theory. It's about, coding claims and generating certificates that convince people that things hold. Interactive theorem proving is another kind of applied proof theory. It's about designing proof languages and proof systems that are practical for writing ordinary proofs. Right. This talk has been about putting them together using interactive proof systems to verify cryptographic proofs. It's a good market for verification. People care about verifying smart contracts because there's a lot of money riding on them. And so, they want to have strong guarantees that the smart contracts are doing what they're supposed to do. The projects have been a lot of fun. It's more fun than I thought it would be. So it's possible to do fun and interesting projects in an industrial setting. There are lots of interesting logical and mathematical ideas involved. And I hope I've convinced you also that thinking about applications like these provide interesting new perspectives on mathematical proof. So let me close with that. So thank you for your patience and your attention.